Well, thanks for inviting me. Dale Sarter here from the Lawrence Berkeley National Lab. Today, we're going to take a look at various liquid cooling techniques and requirements. I guess we can go to the next slide and the next slide. Sorry about, oh, I get to advance this, don't I? Maybe.
You do.
Here we go. So there seems to be a delay, but it's working. Okay. So as I was saying, we're going to discuss some issues, challenges, and in the future, we're going to go from there to a case study at LBL, and then we'll draw some conclusions from that. That'll be followed by a 30-minute discussion session with the leads from the various ACS groups. And I'm not sure how come we're not advancing here. There we go. So the early mainframes computers were all liquid cooled. So as densities increase, we need to return to the liquid cooling concept. But standards are needed for temperature as well as to facilitate multi-vendor solutions. There's significant energy and water savings opportunities. We've been studying this for many years. It started with the chill off, where we compared a number of liquid cooling solutions at that time. And what we found was the closer the liquid gets to the load or the heat, the more efficient the system is. Just for reference purposes, we put in a crack efficiency here, and the lower on this graph, the better. This is kilowatt per kilowatt. And as you can see, there's a significant improvement just going from a crack unit to a craw unit. And then as the water gets closer to the load, whether it be in-row coolers, rear door heat exchangers, and then direct touch cooling, each one of those makes a small improvement or a significant improvement, actually. So the techniques we're going to look at are the computer room air handlers or overhead and in-row liquid cooling, in-rack liquid cooling where the cabinet's enclosed typically, rear door, both passive and active, and then cold plate technology and immersion cooling. And as I said, the efficiency as well as the allowable temperature increase as we go down the list. We're going to start with in-rack liquid cooling. Typically, they're equipped with integral coils and full containment. This often requires some pretty high pressure drop through the cooling coils because the cooling coils need to be compact, but it's a good solution for edge applications. The next technology would be the rear door heat exchangers. There's passive technology, which relies on the server fans for airflow. And then there's active technology that supplements the server fans with external fans in the door. These systems or rear doors can use chilled or higher temperature water for cooling. And as I mentioned, in terms of my argument against a lot of CDUs or heat exchangers in the loop, in order to benefit from the warmer water, say tower water, free cooling, we want to minimize the amount of heat exchangers. On the other hand, we don't want, or we can't have tower water running through our rear doors. I should point out, though, that even if we're using a chiller with the rear doors, it's usually more efficient than crack and craws. At LBL, we have a mix of passive and active rear door heat exchangers. We go to the active rear doors or the ones with fans when our heat density is higher and we need the greater output, especially since we're trying to achieve the cooling with warm water temperatures. The next technology we're going to look at is cold plate cooling. Here we have an example at the Maui Department of Defense Data Center where the system is 90% water cooled, 10% air cooled, and we can cool with temperatures as high as 44 degrees C. The dry cooler consumes about 10 kilowatts, which would compare to about 100 kilowatts had this data center been cooled with a chiller. And I'll add that in Maui, the difference between the wet bulb and the dry bulb temperature is pretty low, so the benefits of using a tower are not really there. So the dry cooler wasn't much of a penalty in terms of our ability to cool with just the outside air. Here's a cold plate variation where instead of the heat exchanger on the heat components directly, this is a plate that covers the top of the server, and heat risers are connected between the hot components and the top of the server. This system was tested at the National Renewable Energy Lab and Sandia National Lab, the server fans were removed, and it achieved about a 90% plus liquid cooling. None of the nodes were throttled back while testing, and it ran between 24 degrees C and 35 degrees C. And the delta T was 7 to 8 degrees. On this slide, as well as on numerous other slides that I forgot to mention, I've provided a reference for additional information should you desire it. In this case, it's a test report from the National Renewable Energy Lab. Another cold plate variation, and I know Shlomo's been chiming in on numerous occasions here, is the running the cold plates under negative pressure. And another test was done at Sandia National Labs, where the racks were 30 kilowatts. It involved a 12-volt DC OCP bus bar. They achieved 70% liquid cooling with a medium temperature supply water of 21 degrees. The return water was 32, and the entering air temperature was 26. Moving to liquid immersion cooling, shown here are three options in the data center. The first one is the natural convection option. The second one is the pump circulation in the tank, and the third one is two-phase. We've been hearing about these earlier today. In this case, in terms of the diagram, we're showing heat dissipation to the ambient via a dry cooler, but that could be a tower or a combination. The facility water needs to be, at least a couple of degrees above the ambient with the dry cooler, that is. So those immersion coolings can be handled in a tank like the single phase shown on the left and the two phase shown on the right, or it can be run in clamshells that are like, that will slide into your rack similar to a server. I guess we had some animation there that I failed to recognize. So ASHRAE, back a while ago, we had a big problem at LBL because we run several high performance computing or supercomputers at a time. And whichever vendor had the lowest temperature requirement for the cooling water drove the design and the operation of our central plant. So that drove us to inefficient cold temperatures because we had to go to the lowest common denominator. So we set up a group in the HPC working group to establish some temperature standards, and later those were adopted by ASHRAE, the W1 through W5. As you can see, W1 and W2 are sort of more conventional, where you'll use a chiller and a cooling tower, and then on the side or when the ambient conditions are good, you could use a water side economizer with either a dry cooler or a cooling tower. So those temperatures range from 2 to 17 with W1 and 2 to 27 with W2. Going to a warmer regime, W3, the goal is to run on cooling towers primarily with perhaps a chiller as a backup, depending on your climate zone. Here, we want to see temperatures available, being able to operate up to 32 degrees. W4 really assumes a water side economizer without a chiller backup. This would be a compressorless system with either a dry cooler or a cooling tower. And here, the temperature required goes up to 45 degrees. And then W5, the concept is for greater use of the waste heat for heat recovery. And those will be in temperatures above 45. There seems to have been some misunderstanding or misinterpretation of these W values where vendors were thinking that if, say, for example, they could cool with 30 degrees, that they would qualify for W3, and that's not true. And I think ASHRAE is going to be making some corrections or some clarification that to achieve a W3, the system has to be able to cool with 32-degree water. Next, so I guess I get to do that. Okay, so here's the typical liquid cooling solution where we have a load. There's a CDU cooling distribution unit between the facility water and the data center water. There might be a chiller in the loop that's cooled by a cooling tower, or as we've talked about in many locations, the data center can be operated without chillers with a water site economizer. So that's what we call free cooling or cooling without compressors. This type of liquid cooling or this type of economizer is the easiest to retrofit compared to, say, an air side economizer. It's important to put the system in series with the chiller, and I'll show that in a second. And again, it can use either a cooling tower or a dry cooler or both to achieve the cooling. So this is a traditional wet cooling system. The heat exchanger on the left is labeled as a condenser, so that kind of implies that it's a chiller. But it could be, another type of heat exchanger and just exchanging heat to a cooling tower. And in any event, the goal would be to have the hot water leaving the heat exchanger at about, in this case, 35 degrees. That would go into the cooling tower where it would be evaporatively cooled to 24 degrees and then return to the heat exchanger. But in many climates, we don't need to use the water that's typically used in a cooling tower. For example, our supercomputer facility at LBL, we have 2 million square feet and over 100 buildings. Our supercomputer center is more than doubling our water consumption because of the cooling towers. So to mitigate the high water consumption, on many days, we can use a dry cooler, and we see more and more installations like this. So in this case, we start with the same 35-degree warm water. Perhaps it's like maybe a warm 31 degrees outside, so the dry cooler only is able to cool the water down to 29 degrees. And then it's topped off from a cooling standpoint down to the 24 degrees going through the tower. So anytime the ambient air is cooler than the hot water returning from the data center, we have an opportunity to use both free cooling as well as waterless cooling. As I mentioned, especially at W5, there's opportunities to reuse the waste heat, but you can do it at other lower temperatures as well. The heat can be used for adjacent offices or other buildings. It can be used for preheat of makeup air in what's called a runaround coil. We can use a heat pump to elevate the temperature. For example, at LBL, we have a data center that we draw heat from in rear doors. So that's a pretty cool liquid cooling temperature, but we elevate it with a heat pump and then use that hotter water in a reheat loop in an adjacent laboratory building. Warm water is also used to heat greenhouses, swimming pools, and district heating systems and other requirements for heat, say, for example, snow melting and that sort of thing. While liquid cooling potential is understood, the uptake has been slow and most solutions are unique and proprietary. So what's needed is an open specifications for liquid cooling, and that's what we're here, I think, talking about with OCP. What that would likely lead to are multi-source solutions and reusable racks and infrastructure, so that typically in our homogeneous supercomputer environment, when we cycle a computer, when it's refreshed, the entire system is removed down to the floor. What we'd like to see is more reusable infrastructure, and users can help drive the transition to those new technologies. So I want to talk about future proofing and an LBL case study. While I mentioned that supercomputers are already liquid cooled and each one is uniquely liquid cooled, but there's a growing need at LBL and other companies and institutions for smaller high performance computing clusters that use more conventional components like server racks. So in our sort of enterprise data center, we developed a 10-year master plan to look into the future at different, and the future definitely calls for liquid cooling. This existing data center or enterprise data center has a lot of legacy and inherited equipment. In other words, a scientist could come to LBL from another institution and kind of bring his servers or his IT equipment with him. So we don't have a lot of choice in what goes into the data center. But then there's also the newer air-cooled but highly dense clusters that I mentioned. These are typically, 1 to a half a dozen racks where all the servers are working in unison to solve a problem. And then we see in the not too distant future the need for very high density racks over 30 kilowatts. So with that in mind, we wanted to have a master plan that was driven by increased density, the need for energy efficiency, and the concern of water consumption as well. Our target was to grow from about a half a megawatt to 1.2. We're restricted on space. It all has to stay in the same space. And the PUE, the existing PUE of 165, our target is to go to 1.2, but a stretch target, if we can, to go to 1.1. The conceptual 10-year plan involves 3 zones. One zone is for the legacy air-cooled equipment. The second zone is for high-density air-cooled IT. And the third zone would be high-density direct liquid cooled. So in zone 1, we'll use conventional air cooling with underfloor distribution, sorry about that, with partial hot air containment using existing crack crack units, water-fed crack units. Here we'll be using basically ASHRAE A1 equipment that's rated for 27 degrees operating and up to 32-degree maximum. In zone 2, we'll use passive and active rear door heat exchangers depending on the density of the rack. The rear doors will normally be supplied with 19 degrees C cooling water, but on really hot and humid days, the temperature may go as high as 29 degrees because our goal is not to have compressor cooling in these loops. We're designing zone 2 to provide ASHRAE A3 conditions, which is 27 degrees normally, but operating up to 40 degrees C. In zone 3 is for our super high density that will use direct liquid cooling. The cooling water can be warmer in this zone than it may draw on the return from zone 2, so that we'll cascade from zone 2 to zone 3. There's a need for a liquid cooled rack standard to design this zone. So again, that we can have interoperable equipment and equipment that will last through several cycles of refresh. So I mentioned the cascading concept, and the table on the upper left sort of is a summary of the temperature requirements for these various technologies. The CRAW units, computer room air handlers, they're normally going to require 6 to 18 degrees C water with an extreme of about, around 21 degrees. So that would be a class 1 in the ASHRAE classes, and it's our zone 1 at LBL. The rear doors will operate between 18 and 23 degrees C with an extreme of about 29. So that's a class 2 or 3. And in our data center, that'll be our zone 2. Cold plate is 18 to 45 degrees C, or I'm sorry, 18 to 40 degrees C with 45 degrees as the extreme. Here again, it'll be a W class 3 or 4 in our zone 3. And then immersion can even go to a higher extreme temperature and is also a class 4 and 5. Now, these temperatures are typical. Individual systems and components vary with both the normal inlet temperature as well as the extreme. Some designs push the boundaries, but in any event, the idea that it's going to take cooler temperatures to use a CRA unit and warmer temperatures with cold plates and immersion is the given or the point that we're trying to make here. And the second point is that we can cascade. In other words, the effluent from one class can become or one zone can become the input to another. And thanks to Rolf for providing some of these more detailed graphics of system designs where the temperature cascades in the data center from cool to hot, so that you significantly increase your delta T. It reduces pumping horsepower and it increases the efficiency of the cooling plant. I should mention that cold plates and rear doors running at elevated temperatures may not remove all the heat and may require lower temperatures and a secondary removal process, or it might require a reduction in compute performance. So for example, for us, we may have a few very hot and humid days where our temperatures, say to the rear doors, run warm or warmer than desired. And in those cases, the outlet air temperature might be high, which then becomes the inlet temperature of the IT equipment. And the equipment may reduce its clock speed in response. And we've chosen to accept that penalty in exchange for reducing the capital costs associated with a compressor-based cooling plant, reducing its complexity, and also energy efficiency. So in conclusion, we need to move to a compressorless cooling, and we can. Water conservation and heat recovery are further goals of liquid cooling. But facilities need to be equipped with a warm water loop. If you're looking at a chilled water loop in your building and the data center is just one component on that chilled water loop, you get some benefits, as I mentioned, but not as many as if you have an independent loop that can depend on or can utilize the warmer temperatures and more hours of free cooling. As I mentioned, for us, the benefit of not having a chiller plant is efficiency, reliability in terms of reduced number of components, simplicity, and a lower first cost. You can start with a water-fed crack unit. That's what we have. So once you've got that loop of say tower water or dry cooling of a loop, the water-fed crack units can easily run on that. So that's a conventional system. You can move to rear doors. Rear doors are a great transitional technology, and then ultimately you can utilize that same water loop for cold plates or immersion cooling. So we're going to talk about that in our panel discussion coming up in a minute here. For our call to action, I urge you to attend the Advanced Cooling Facilities track that's going to occur Thursday morning Pacific time. Consider liquid cooling in upcoming data center projects. Be aware that it's not an all or nothing proposition, but a plan and the need for adequate infrastructure. Volunteer to help OCP make a difference in accelerating high efficiency liquid cooling in the market. You can do that by joining the ACS groups, and all three of them are listed here: rear door, cold plate, and immersion. And then also you can join the Advanced Cooling Facilities sub-project work stream that I provide the link for as well. So with that, I'll conclude my presentation, and should we take some questions?
Hey, Dale, thanks so much. Yeah, there were a couple of questions and comments that came up in the chat. One was from Rolf Brink. Rolf, I see that you're on the call. Do you want to discuss with Dale?
Yeah, Dale, I just want to apply a little correction on where you refer to me as the source as well on the slide with all the temperatures. Sorry. The temperatures and temperature ranges that you showed, they're not industry-wide references. They're case-specific references for a specific, in a paper that illustrates how you can deal with specific requirements. So the tolerances are not determined by the technologies, but by the IT specification that the technology at that point in time is cooling.
Yeah.
Right, so right now there are cold plate solutions that are able to deal with 65 degrees C cooling, and there are immersion platforms that require 20 degrees Celsius cooling.
Yeah.
Right. So it's all over the place. It can be anything. So it's not an industry-wide reference, right?
Right. Well, actually, Rolf, the table was mine. It started with one of yours, but it had my data in it. But I do agree that there's not sufficiently available statistical data to make those values scientific. That those are typical values that we've seen, and I made the point that it could be that is plus or minus, that specific components and specific systems run at different temperatures. But those are some ranges that we've seen in our experience. But the important thing that what I did credit you for was the cascading, the more detail in terms of how to plumb a data center so that you can reuse the effluent from one liquid cooling system to become the input to another liquid cooling system.
Yeah, and I think that's one of the key factors going into the next stage with the industry when we're looking at drastically increasing efficiency across facilities. It's not only for the purpose of reuse, but also if you look at your own facility and what you just described with the different temperatures, whatever requires the lowest temperature cooling doesn't have to be the common denominator for all the platforms. But if there is a way to creatively work with these building blocks and cascade that thermal energy across multiple platforms, then all these platforms can sit within their own comfort zone, and you end up circulating a lot less liquid, which is much more efficient to cool because it's much easier to cool down 100 liters of liquid from 50 degrees C to 20 than it is to cool 500 liters of liquid in a delta of 6 degrees.
Right, and as I mentioned, when you have your free cooling in series with your compressor-based cooling, you'll get a greater percentage of the cooling the warmer the return water temperature is. I mean, I think the vision is to run our data centers so warm that we will use no electricity for compressors and no water for evaporation, that we can cool anywhere in the world just from the ambient air. And I think that'll be a vision that we'll see if it's reality as we go into this panel discussion phase of today's session.